Well, I think we can get started. Welcome back, everyone. Looks like we're mostly here and people survived Halloween, so that's good to know. I hope you all had a great Halloween. But any questions at all, folks, before we get started today? Okay, well, my announcements are we're in section 4.9, and that means we're at a very, very special part of the course. We're about to bridge the gap between the differential calculus that we've been doing essentially all along and the integral calculus that we're going to begin in chapter 5. It starts off kind of slow, and this section, areas and distances, by analogy, it's no different than this section, where we were drawing tangent lines for the very, very first time. So in that section, we're trying to set up things initially, just like what we did over here. That means it's kind of a lighter section, but that's what gets everything kicked into motion, where we begin integrating instead of finding tangent lines. If you're curious what we're really doing when we say integration, geometrically, it's going to look like this. We'll put down a lot more pictures, but here's a really quick note. If you integrate from, let's say this is value 1 to 5, let's just say it's those values, then all you're trying to do is find the area that's under this curve going from 1 to 5. So integration is just trying to find area under this curve right here. Differentiation is more about tangent lines, specifically trying to get that slope. And in some really, really weird way, these problems are related, extremely related, to the point of sometimes people say that one is practically the opposite of the other, although that does require a couple extra statements to make that a little bit careful. But that's what we're getting into in chapter 5. Again, that makes section 4.9 really, really pivotal that we're taking a look at right now. So let's take a look. The supporting document is going to be the differentiation formulas. And essentially in this document here, every single rule or maybe table of derivatives like these especially, these are all antiderivative formulas. When we go left to right, we're taking a derivative. But if we go right to left, we'll say that the antiderivative of cosine is sine x. So these tables have two purposes. And so it becomes probably this document right here, one of the more important documents in the entire course, especially if you know you're going on to Calc 2, Calc 3. And Calculus 2, they're hitting the ground running. It's kind of rough. You have an advantage going from a fall semester to a spring semester. It's a disadvantage doing Calc 1 in the spring and then Calc 2 in the fall because of that summer gap. But Calc 2 hits the ground running, and knowing these down pat, being ready to go with them, is probably the best thing you can do to be successful in Calculus 2. We'll mention that as we get through the problems, but so far, that's what we're going to be working on, section 4.9. And then we have our third exam that we're going to be taking a look at. It's only going up to section 4.7. And like we mentioned before, 3.839 and 4.7 are all application sections. I'm only going to ask a question from 2 of those 3, and I'll use a random number generator to do the picking. Don't forget also for that exam, you're allowed to have a calculator of some form. It can't be a graphing calculator or something that connects to the internet like a cell phone. And you can have a single page of notes front and back. Always a good idea to do those early. And for the assignment number 11, because it's not on exam number 3 we're up to, we put an extension on this due date as well. They'll be due the Monday after if you decide to prioritize those specific sections. Well, I think that's my full spiel for the day. Let's get started with 4.9. I forgot to open it. It's right over here. So those are the initial colors I'll be using in the color coding. We're going to think of f as the original function, and we're looking for an antiderivative. And all the antiderivative have to satisfy to be correct is the derivative of your antiderivative must be the original function, and that has to work for all x in the domain of that original function. Let's do a really fast example. This will be an example of verifying if we have an antiderivative. Let's say let f of x be equal to, let's make it be, say, 3x power 5 plus 6x minus 11. So I'm claiming this is an antiderivative for some function, and we can find that function, f of x, immediately by differentiation. And in some sense, this is backwards. The way the problems are going to go is they're going to give you the function f of x, We're going to try to find the antiderivative. But this example here, just for the purposes of highlighting how the definition goes. So if we calculate f prime of x, here's what it'll come out as. Just an ordinary derivative here. 5 comes down, multiplies the coefficient. It's now a 15 times x to the power 1 less, power 4. Derivative of 6x will give us just a 6. The derivative of the constant doesn't influence it at all. That goes to 0. And so that's our f of x. So that means this thing is the antiderivative of the f of x function indicated right here. Now we have to imagine if we were given the original function, how in the world do we get to the antiderivative? Well, we pretty much just use our differentiation formulas and we go backwards. We would use this power rule, but we have to reverse the power rule. And that's kind of our goal in these notes, is just to refamiliarize ourselves with these major objects that we've been using and see how we can make it go backwards. So that's going to be our next step. But the next thing we should talk about first is, when we look at this problem, notice this part is extra special. We could put anything there, as long as it's a constant. You could have put nothing at all. Now, everything on the screen is still totally correct. You could have put minus e to the power of 101 for no apparent reason. It's still correct. And so there is more than one antiderivative. And it's almost not even appropriate to say the antiderivative. That's the definite article trying to say there's exactly one. We should really say this. An antiderivative of f of x, there are infinitely many of them. They all differ by just a constant. That's just the fact that if you differentiate a constant, it goes away. So when we go to find an arbitrary antiderivative, here's what it's going to look like. The most general or the most arbitrary antiderivative of f on an interval I has this form. Let me redo the highlighting here. It'll be your antiderivative plus an arbitrary constant c. We're later going to say that that's the constant of integration. We can say it here now, just as a reminder. Sometimes we say c is a constant of integration. So back up to our really fast example up here. Instead of putting a constant, a specific one, this is what we're really going to do. We're going to put plus c. Now that represents any real number whatsoever. If you differentiate that c, an arbitrary constant, you still have the right answer, and it still shows this f of x in blue is the true antiderivative of f of x in green. So that's the process. And this constant here is worth exactly 1 point. Whether it's on homework or exams, it turns out it is pretty dang important. There's certain things you cannot solve correctly without putting in that right constant. Notably, differential equations goes haywire if we're not inserting these correctly. And so it becomes really, really important. It warrants a reminder every time. And so if you notice I forget one, please just yell it out, and I'll be sure to write it in the notes. Sometimes I forget too. Well, that's what this looks like so far. Let's put down here just a really fast problem to try to figure out here. Let's say for a really quick example, let f of x be equal to 1 over 3x squared. Find the antiderivative of f. So those are typical instructions you'd see, and these instructions themselves are pretty confusing. When it says the antiderivative, that's weird. There is no the antiderivative, but what the instructions are really trying to get us to do is write our answer in this form. We're trying to write the most generic antiderivative, the most arbitrary one, by inserting that constant c. So let's give this a try. First thing you might want to imagine if you're dealing with this is, well, how would you differentiate it first? You would never want to use the quotient rule on this thing. You would change its form. So let's do that right away. We're going to let f of x be equal to 1/3. There's the constant, and the constant multiple rule is still in play for antiderivatives. X here is in the denominator, and so even if you're differentiating it, we need to move it up. Let's make it be x power -2. Now, we're not differentiating it, but even the antiderivative, that's a really, really strong thing to do, or a really sound thing to do to get through the problem. Now, here's the formula that we're going to need. We're going to need the power rule, but we need to fine tune this thing. We need to turn it around and make it work for us for antiderivatives. So first, let's study what it does for a derivative. If you differentiate x to power n, first, n comes down. Put a number on that because that's step 1. You put it down, and then step 2, you multiply. I'll put just mult here. Then step 3, you decrease the exponent by 1. I'll just use the arrow there in step 3 to indicate that. So let's reverse the whole thing. We can say here, the antiderivative of x to the power of n is, now if we're reversing everything, we really mean it. We start here on step 3, that's our new step 1. Let's write down x. On that step 3, the power went down. So for us, we're reversing that too. The power goes up. It's n plus 1. Already, that's going to be something to get used to. If we're reversing the directionality of the power rule, we're not subtracting 1 from the exponent. We're adding 1 now. So that was our step 3. Now we go to step 2. We're not multiplying. We are dividing by that thing. There it is. Then we just throw it in. For our step 1, it goes into that location. So that's what happens if you use the general rule, the power rule general version, but reverse it all for an antiderivative. We get that as a result. And the way we know is true is, here's the check. You take x power n plus 1, divide by n plus 1, differentiate it, and here's how it's going to go. N plus 1 can stay right where it's at. It's just a constant, so it doesn't move upon differentiation. Then we differentiate x to the power of n plus 1. N plus 1 comes down. New power of x is 1 less, so now it's n. And it goes back to x power n, like we're expecting. So that tells us that it's the right formula. Let's put it in a box just to emphasize it. Kind of a weird looking box. And that means we can go back to our original problem right up here and find that antiderivative right away. We'll say, oh, I'm pointing here, but we want to look right here where we put it in the right form to find the antiderivative. We'll say f of x. If you use this notation with uppercase f of x, you now are talking about the antiderivative in this section. First, the constant multiple rule doesn't change that constant no matter what direction you go in. Derivative or antiderivative, that stays put. Next, I'd write down x, but a little bit of space before the third. We go up here, the power goes up. So take -2, add 1. It's now a -1. So that means we need to multiply, or excuse me, we need to divide by that power, or multiply by the reciprocal of it is what I was thinking. Good thought if it was a fraction. This is 1 divided by -1, like that. So next step, we simplify. This is now -1/3, x power -1, and the whole problem would stop right there. But the moment you do an antiderivative, the check definitely is not just for show. It turns out it's really important. I wouldn't take off a point if you didn't do the check on a homework problem or an exam problem, but I would say if you're doing homework problems especially, have 2 sheets out. One sheet is the thing you're going to hand in. The other sheet could just be generic scratch paper. On your scratch paper, I would highly encourage you to do this check. Definitely differentiate your answer. You're doing 2 things at once. you're going to need to have these derivatives down pat for Calc 2. So this is a huge help already for that. And plus, we're better at differentiation than antiderivatives, and differentiation is fast. So that's a really fast check. We shouldn't leave that on the table. If we differentiate this, what would happen is -1 comes down and multiplies. It's now 1/3. Then we subtract 1 from the power of x. It's now -2. If we want to, we could correct that to make it look like the original function. This would become then 1/3 x squared, which was the original f of x right up top. So the check, again, it's really important. It's so easy to catch a mistake if we just differentiate it. And also, it's going to keep us in top shape for getting through Calculus 2 as well. So that's our initial spiel on what's going on with antiderivatives. What we're going to be doing next is just practice a whole lot of these and start collecting more formulas. Any questions at all, folks, so far with getting through this first initial example? Yeah, go ahead. Oh, good call on that one. I totally forgot it. The plus C should have came in right here. Ed, not finding it, I would have done this on the homework paper, -1, and just emphasized it a whole bunch. So thanks for spotting that. That's definitely worth emphasis. If it was a homework set that you turned in and you forgot plus C on every single problem, I'm not going to take off a point on every one of them. I'll just make a comment on every one and take off a point once. Similar for an actual exam as well. But other questions so far about that? Okay, thanks for spotting that plus C. And on the check, it's weird because we'd still differentiate that as normal, but the derivative of the C goes to 0, so our check is still, it would look the same. Well, let's try out another one just to get a feel for more of these. Here's example 1. We're finding the most general antiderivative, and that's just reminding us, don't forget about that constant C. Easy to miss. So when you do these kinds of problems, let's let our first one go like this. F of x is a function that reads 2x cubed minus x to the power of 4.7 plus cube root of x power 4 plus 12. So that's our entire function right there. We want an antiderivative for it. We can go term by term, just find antiderivatives of each of the component terms. It's just like doing this problem up here once for every single term that we see there. But some of the terms are not as nice as the others. 2 cubed is very nice. This looks weird, but it's absolutely okay. We're using the power rule, so we just want x power n to be in the numerators. That one's all mixed up. We should fix this one if we see a radical function mixed with ordinary exponents. So our first official step would be to write f of x equals 2x cubed minus x to the power 4.7 plus x to the power of 4/3 plus 12. So now we're in really great shape to get through this problem. We'll indicate an f of x, capital 1. This is going to be our answer, the antiderivative. And we're just going to go term by term. But the first thing you want to do is bump up that power. So I'll start by writing down the constant. It's unaffected. Then the next first real step here is the power 3 goes up to power 4. Then after you've increased that power, excuse me, take that new power and immediately divide this time. So it'll go right there. Then it's rinse and repeat. Here I'm going to write a minus and then a little bit of extra space this time before writing down the variable x. New power on this one will be a 5.7, adding 1. And so I just threw in that extra space to put in 1 over 5.7. For these kinds of fractions, 1 over 5.7, you could do a lot of work to simplify them, get a fraction form out of that. I'm okay if you just leave it in that generic form or throw it into a calculator. I would almost say this is better since you don't have to worry about rounding it at that point. It's an exact answer in that format. Then rinse and repeat, we'll do it all over again. It goes plus. Let's put in a plus, a little bit of extra space before the variable x. And any volunteers for the new power on that variable? Exactly, we're going up, so add 3 over 3, it's 7/3. And what I wouldn't want to do here is, let's not go 1 over 7/3. That's just giving us an extra step. We would have to simplify that. Instead, division by 7/3 is multiplication by the reciprocal. Let's just go to the punchline and put 3/7 in right away. Next, we have a 12 here. Any volunteers for what we should write down for the plus 12? Not quite, but we definitely do need it right here on the far right. But we still need something for the 12 itself. Exactly. There's really an x there. We can temporarily insert it just to illustrate. It's x power 0. Kind of silly, right? The power of x goes up by 1, so it's 12x power 1, or just 12x. You're dividing by 1 the new power, but that's no change. So if you see a constant, the goal is you just write down the constant and the variable from the problem. So we just tack on an x to that. Then good call. Thank you for reminding me of the constant c. That's definitely something I struggle with remembering. Plus c has to go there as per the instructions. So we did it, folks. That's our antiderivative. Looking at it, that's the only thing I would want to simplify, the 2/4. Let's take the time and write that out nicely. 1/2 x power 4 minus 1 over 5.7 x to the power 5.7 plus 3/7 x to the power 7/3 plus 12x plus a constant. Now, again, the moment you form that antiderivative, let's do the check. I'll just put it here in parentheses and use the orange pen. We're doing f prime of x. And here's how this would go. 4 comes down, multiplies a half. So a half times 4 would just be 2. X goes down a power, so it's cubing now. And this one just looks designed to work out, right? 5.7 comes down, it cancels a fraction. It's just a -1. Power goes down by 1, it's a 4.7. And 7/3, honestly, great way to memorize what should go here is, it needs to be the thing, so that when 7/3 comes down and multiplies, it clears off and gives you the coefficient of 1 that we're expecting up there. That would happen, that'd be 3/7 times 7/3, so it'd be plus x. We would subtract 3 over 3, so now it's 4/3. Now it's getting fast. Derivative of 12x is 12. Derivative of the constant is 0. Forgot to write. Then double check with the original function f of x. 2x cubed minus x 4.7. And I don't have that specific form, but we know it simplifies to x 4/3, so we're okay there. Plus 12. That says we've got the right answer. And that's our first antiderivative down. Any questions at all, folks, on that one there? Okay, I won't show the check on every single problem, but definitely on the weird ones, we'll try to emphasize it on these notes as we go through the problems. So that was our first one to try out. Because this problem is very much just getting familiar with taking antiderivatives, we'll try a bunch more. So here's what another one could look like. For part B, let's let it be the function that goes f of x equals root x divided by 2 plus 2 over root x plus cosecant squared of x. And we can go from there. So we want the antiderivative of all this stuff. The root x and the 2 over root x, those are actually the worst part of this problem, I'd say. We need to do some exponent work on these to get this to work out. And so my very first step would be rewrite f of x in this way. Instead of root x divided by a half, that's kind of confusing what the differentiation formulas even are. Let's pull out the constant. It's really 1/2 multiplying root x. And root x is just a rude way to write your exponent if you're finding derivatives or antiderivatives. We should put in a power of 1/2 instead. Then rinse and repeat. Here the constant is 2. So it's plus 2. Down in the denominator, it's x power 1/2, but we need to bring it up. So it's really x power negative 1/2 right there. Does that make sense to folks on what happened to that poor root x? Awesome. So that one's done. It's ready to go. Cosecant squared x. There's not much you can do to that. But the moment you see a trig function, here's what we should do. go to your differentiation formulas document. Again, this is right on Moodle, right under the 4.9 notes. And we're just looking for information we need for this problem. We've got natural exponents, we've got exponential functions, but we need the trig table, and we need, let's see, cosecant squared appears right here. So the way we're going to work this one is we'll take this formula. Let's just drop it down into the problem. But when we reverse that, notice we're doing positive cosecant squared. There's a negative there. That's actually okay. We can think of this in these terms. Every one of these differentiation formulas can be re-expressed into any format that's just convenient. Not sure where I'm going over here. Let me go back over here. So we can take this and say, well, d by dx of negative cotangent x. Well, we will copy the negative sign. Derivative of cotangent is negative cosecant squared. So that negative is going to cause a cancellation and get positive cosecant squared of x. It's now a brand new formula. And we get an extra negative sign right here in that sense. Or you could think of it really just as there's a negative in the cosecant squared. We're just putting it back here when we find the antiderivative. Either way you think of it, here's what's going to happen. Uppercase f of x is going to be first, let's copy that half down. Give it some extra space before the variable x. Add 2/2 here. New power is 3/2. We come down and we're going to divide by 3/2, which is multiplied by its reciprocal, 2/3. So times 2/3 here. Then back to rinse and repeat. So +2, a little bit of extra space for variable x. Adding 2/2 to -1/2 gives us +1/2. And so dividing by +1/2, that's just multiplying by 2. So I'll just go times 2. Or 2/1 if you're thinking reciprocals, but it would come down to this either way. Finally, this is the trick one. Antiderivative of cosecant squared. I'd be looking here on the table. And the moment I see that, well, there's a negative sign here, I'm putting the negative with cotangent and writing in negative cotangent right in that spot. Then here's the thing I forget a lot. Don't forget your constant c to finish off the problem. It's easy to get excited on the interesting stuff like that antiderivative, but this part is still important. Well, I think we've got it, folks. Any questions on this antiderivative? Okay, let's do a check on this one. Oh, let's do a simplification on this one, and then we'll do a check. We need to simplify all these coefficients out and say f of x is now 1/3 x power 3/2 plus 4 x power 1/2 minus cotangent x plus c. And that's finally our answer. Let's see if it works out and do another fast check on this thing. Now we're just differentiating this thing, so we can write f prime of x equals 1/3 copies in by the constant multiple rule. We multiply by this exponent when we're differentiating, so 3/2 goes here. And then we subtract 2/2, so now it's at power 1/2. So we're trying to get to that term, and that would qualify. I would put a check here. I wouldn't want to do a ton of steps on the check. Just look at it enough until we can see, yes, they do match up with what we want to do. And the more you do these checks, sometimes people just stare at it and imagine, okay, 3/2 comes down, the 3's cancel, it's a 1/2, that matches, and subtract 2/2, that gives us a 1/2, it matches there. Sometimes people just eyeball it for a while until it looks like it's correct, or we find a mistake. But writing it out is definitely a good idea to do the first few times. Let's differentiate this term. Plus 4 times a 1/2, subtract 2/2, goes down upon differentiation, now it's negative a 1/2. And this would turn into a 2x negative 1/2. That means it works. It's exactly that upon simplifying. And that takes us to the real meat of the problem. This is the major reason I would check it out. That just kind of looks fishy, even at looking at the original formula or the adapted formula up here. So let's differentiate this on our own. I'll put in a negative sign. Derivative of cotangent is still negative cosecant squared x. these signs would go positive, so we get positive cosecant squared x. That means it matched up. We have the positive value that we're expecting right up here. The constant here goes to 0, so I would say at this stage, we put a check there just for the sake of parallelism, it matches f of x, and the whole check is over. Well, any questions, folks, on satisfying that check down there, or the main problem itself? Okay, trig functions are definitely kind of weird on this, but the goal, if you see a trig function, is to always look towards the right-hand sides. If a cosine comes up, its antiderivative is sine. If a sine comes up, its antiderivative is negative cosine. That will be confusing, so we'll make a big deal out of it every time we cross that bridge. But certain things don't come up. For example, you never see a tangent squared here, but you see secant and tangent. So some derivatives are just extra tricky. Let's do one of those extra tricky derivatives just to see how it goes. Trigonometry is a great source for that kind of material. And this trigonometric one will go like this. For part C, let's let f of x be equal to, and I have a specific one here that's just awful, 1 plus tangent squared x. Now looking at this thing, we could start by getting antiderivative because the antiderivative of 1 is x. But then we get stuck right at that step. I do not know the antiderivative of tangent squared x right out of the gate, and this table is not going to help us. Tangent squared does not appear at all. In fact, the only functions squared that appear are cosecant squared and secant squared. This table doesn't even help us find the antiderivative of sine squared. Antiderivatives turn out to be pretty hard. But yes, go question first. It wouldn't help too much because if we took the derivative, we would be 2 antiderivatives removed. There wouldn't necessarily be a strong connection on getting to the antiderivative on this one.
Then can we rewrite it as 1 plus tangent?
We could, but undoing the product rule turns out to be pretty nasty on its own. Actually, that's where calculus 2 starts. They call their first section 7.1 integration by parts, and you're undoing the product rule. But it turns out that's a pretty hard process, even if it was this problem in that section. But there's still something we can try. Yeah, go ahead. Not quite, because then we'd be looking at undoing a quotient rule in that case, if we had a quotient in. It is a trig identity. I think your folks are getting in on the right thing. These are the bad ones. I would never put this out on an exam without a hint, because you would just have to know that this is the identity that's in the background. But it could happen on the homework. So if you are stuck on a problem like this and you're not sure what to do, just email me, say, hey, Mike, I don't see the antiderivative of this at all. Is there some other formula I can use? And I'll be very happy to help out. So let's start off. It turns out 1 plus tangent squared x is a Pythagorean identity, and it's really equal to this. Secant squared of x. Let's write down that identity. 1 plus tangent squared x is secant squared x through the Pythagorean identities. And that means suddenly that's on the table. Antiderivative of 1 plus tangent squared is tangent. That is really, really weird, right? But let's go through the motions. Now that we have the function down, we can say, we go back to blue, f of x should be equal to tangent x. It's not the whole story. Don't forget the arbitrary constant of integration c. And there's not much more to do on this. If I was to check this, this is pretty much all I would do. Pretend the red dot's my finger. I'd look at tangent x. Well, look that up. Derivative is secant squared. That matches the f of x, which is just a different format of the original function. So the check is immediate on this one, but again, it's like one of those terrible problems where you have to think of a conjugate to simplify the limit. Here, we had to think of a trig identity to get the antiderivative. Any other questions, folks, on getting that antiderivative? Okay, let's try one that's slightly worse, but not bad. So part D, it goes f of x equals 1 over 2 times x squared plus 1 minus 30 times 1 minus x squared to the power of negative 1/2. This is really bad. Yeah, go ahead.
Not usually use L'Hopital's rule to find the derivative of tangent.
For the derivative tangent here.
Yeah.
Well, in these kind of problems, you'd only want to use L'Hopital rule if the problem itself started off something like this, limit as something goes to some value. But if there's no limit in the problem, we couldn't use L'Hopital's rule to navigate through it, unfortunately.
So you can decide limit, do you use L'Hopital's rule already?
We then have to decide, is it in an indeterminate form? Essentially, it would have been a different question if L'Hopital gets involved. The question would become a limit question as opposed to an antiderivative kind of question. Other questions so far? Okay. Now this is really, really bad. We don't want to try to undo a quotient rule. In fact, Calc 2 doesn't even talk about that. If there's a quotient, we rewrite it as a product and use integration by parts to undo the product rule. That's kind of weird already. So this is really, really bad when you see it. The moment you see weird functions like these, we need inspiration. So we start scrolling through this list. This is exactly what I would do. That's not going to help us, but logarithms are getting close. 1/x, it's matching a rational function at least. We saw more rational functions here. Anyone see anything on this list that could help us out? Maybe with just the first thing or the other one if you see the other one. Sorry, say again. Yes, there's an inverse sign right here. 1 minus x squared to power negative 1/2. That's just a silly way of writing this out. There's a sine inverse just hiding inside there. Anyone see the other one? It is a 1/1 plus x squared, written in that format, reminds us of arctangent. Here it's just sort of hidden, right? So good eyes, folks, it's going to be those antiderivatives. You know what, let's copy in this whole table just to emphasize it's all important. And these are some of the tougher derivatives and antiderivatives. So with that whole table ready to go, this would be my next step. Let's make sure we got the right antiderivatives by reformatting the function itself. We can say f of x equals, there's a constant here we don't need. We can put it right here and just use the constant multiple rule, even in the antiderivative. The rest of it is 1/1 plus x squared. I like that format only because of that right there. That's the only reason I would write it that way. It just reminds me of it. Over here, we can leave the negative 30 right where it is. We're going to do some exponent work on this. The base 1 minus x squared can now go to the denominator. That's going to make the exponent positive 1/2. But positive 1/2 is a root. So we get the root of 1 minus x squared down in the denominator, just a 1 in the numerator. That means we're looking at this. But you know what's really wild about these things? We actually made a choice. If you wanted to, and I'm going to revert the notes, we could have put positive here, negative here, and correct answers could be cosine inverse. It's the right antiderivative. How do we know which thing to do? Well, you differentiate your answer. It's going to come out the same either way. You will get back to the original function, whether you use cosine inverse or you use sine inverse. Really kind of weird in a way. So sometimes when you find an antiderivative, a literal choice really was made on which way you want to write it. So put a negative there. Now at this stage, it's a much more clear which antiderivatives we're really using. And we go like this. That's the punchline to an antiderivative. You're reverting the differentiation formula. So f of x is then, there's a little bit more to the story, right? The constant 1/2 stays right where it is. This is arctangent. Let's write that in as arctangent since you said it that way. You don't have to put it in as tangent inverse. You could use an alternate notation, arctan, and you're saying the same exact thing. It's arctan of just x. Over here, copy in negative 30. Over here, this is arcsine, but we can say sine inverse. Let's let both notations work for us. Sine inverse of just x. Then finally, our arbitrary constant c. So that's how that antiderivative goes there. And there's so many more that we could talk about. I mean, we spent multiple weeks looking at all the different formulas that are on this document. So think of this section 4.9. It's not going to be our first rodeo with this stuff. We'll be looking at antiderivatives in chapter 5 a lot after the initial sections 5.1, 5.2. So we didn't hit on everything. There's some really interesting formulas here. For example, if ever a 1 over x occurs, its antiderivative is natural log x, but we're going to use that in a very different specialized way in chapter 5. We're going to expand on that formula. In fact, let me write down a related formula as well. This formula is true, but so is another one. D by dx of the natural log of the absolute value of x is also 1 over x. This was an example in somewhere in the book. The author proves by breaking down the absolute value function into two different cases, when x is positive and when x is negative, he differentiates both of those cases, and you just get a 1 over x. And so this becomes a nasty formula. Not as big of a deal in 4.9, we're just getting started, but in chapter 5 and 6, and really the rest of this entire book, chapters 5 and onward, let's say it that way, if you have an f of x equal to 1 over x, this is the one time we can't just write it as x powered -1 and correct the exponent. If we tried, here's how it would go. Antiderivative of x powered -1 by the ordinary formula would increase that power by 1. It's now x power 0. We take that power of 0 and we have to divide by it, but now we've broken math, right? You cannot do that at all. There is exactly one exception here, and it's this thing. Antiderivative here goes like this. F of x equals the natural logarithm of the absolute value of x plus an arbitrary constant c. Wild stuff. So I'm not sure why it must be this way, but mathematics, when it comes to a logarithm and 1 over x to power 1, has an extremely odd exception. A power rule here breaks down immediately and fantastically. You divide it by 0. So although we haven't hit on every single formula in this document, we definitely will by the end of the course. But I want to highlight this one even before we get to chapter 5, because it's a wild formula. Any questions at all about it, folks? Okay. Well, with what we've got going on next, here's the topics we're going to finish off the class with. We're going to solve some differential equations. It sounds horrible, but we have just the right tools to do so. And in fact, we've already looked at that when we were looking at exponential growth, exponential decay, Newton's law of cooling. Those were differential equations. Here, the goal says solve for the function f. And this is what the problems look like. Let's put f double prime of x equals 7x minus 1. We want to solve for the original function f. Let's write that in blue, because what that reminds us is we're looking for antiderivatives, but our antiderivative this time is twice removed. That's a second derivative. We have to take an antiderivative once to get to f prime, twice to get to the original function f. So we're solving a differential equation because that's a second order derivative set to a function, and we're solving for an unknown function, f of x. But you know, it's really not too bad. What we'll do for this thing, let's call this a part A. Just try to decide on a color. Let's maybe go green and then blue. First thing we do is peel off one derivative. Let's write f prime of x. And that's already an antiderivative. So over here, new power of x is going to increase. It'll be x squared. So copy the coefficient of 7, write in an x squared, then immediately divide by 2. Now for the negative x, or excuse me, for the -1, we'll write negative x. That was weird. I said what we were going to do, not what we're looking at. So that's our antiderivative there. And then one more thing we have to do. This time it's really, really vital. Anyone see what it is? Good call. We have to throw in the arbitrary constant of integration, or of finding an antiderivative.
So for the next antiderivative, would it be CS?
It would be a good call. This c is no different from the -1. So we'll get a c times x on the antiderivative of that. And we need a new arbitrary constant. We can't call it c anymore because our constants could be different value. Other questions so far?
How would you ever find that number C, or would it not be given to you?
They would have to give us initial values, and that's going to be our part B on this example right here. So we're going to look at one with no initial values. We're coming up with a family of infinitely many different functions that all depend on a choice of C. But on the next problem, we'll give initial values and we're going to solve for the constants C and D that we come up with. Other questions so far? Okay, well, for now, we need a new antiderivative. Let's call this f of x. This will be the original function that we're looking for when it says solve for the function f. And so this will also be our last step. Let's write this out. First, I'll copy in 7/2. A little bit of extra space, then the variable x. So new power is 3, so multiply by 1/3 between the 7/2 and x cubed. Same order of business here. It's pretty much just going to become a -1/2. The new power of x is 2. And here's always a good strategy. Every time you write down a step for the antiderivative, you could just do a visual check right here. Differentiate that here and now. 2 comes down, it's -2 divided by 2, giving us a -1, and the new power would be just 1. So if we check it turn by turn, that's not a bad way to just decide if we're on the right track. The next one, constant C, like you mentioned, is going to turn into a CX. I'd probably make one extra step, and let's simplify that situation. Oh, hang on. Let's do one extra step and make sure the answer is right by adding a new constant of integration. Every time we find an antiderivative, this is what emerges. And it's just a consequence of checking your answer. Anything can go there when you differentiate it. It'll go to 0 and make this line correct. Differentiate CX and you just get C and so on. And then last step that I was trying to go for before reminding ourselves we need that constant is to put in 7/6 x cubed minus a half x squared plus CX plus D. And then that's the end result on this one. So we did it, folks. We solved the differential equation from scratch all ourselves. Probably our first one, I'd say. In the exponential growth decay notes, that differential equation was supplied. We just verified it. Well, let's try it out again, but with initial values. First, any questions so far?
So will that be any letter, or is it?
It could be any letter, yes. If you put C, then that's the one thing that could potentially lose us a point on this. If you subscript it, it could fix it, yes. If you leave it at C, you're implying whatever you choose here, you're making the same choice here, but you could go 1, 2. So if you like subscripting, that's a great way to go, especially if you're taking like 90 antiderivatives, 90 different constants, you pretty much have to use subscripting at that point. Other questions about that so far?
For the implementation, would you write capital F?
Well, because they're saying the original function f this way, I would still use lowercase f of x, but I see what you're meaning. Here we're supplied a lowercase f of x, but we only use capital F of x because we're taking the antiderivative of that function. So if we went, let's say, one level further and found a new antiderivative from here, that's when I would use the capital F notation in that case. But since we're only stopping right here at f, I think it's more normal just to use lowercase f of x. Exactly, that's how this new notation is working in these kinds of now differential equations. Other questions so far? Okay, let's try out another one. This one is special. It's a differential equation as well, but it's also called an initial value problem. In fact, all the problems in section 3.8 were initial value problems. We had a differential equation and initial values. We said the initial population is 50 cells, population at time 2 hours is maybe 78 cells, something like that. Those were just initial values in the problem. And so the differential equation starts off by, it's another f double prime of x equals 3x squared minus 1. And our initial values are f at 0 has to be exactly 1 for this problem. Or excuse me, I put in f prime at 0 has to be exactly 1 in this problem. We have to make sure what those primes are. And the next one is that f at -1 is 10. So we have information about the first derivative, and we have information about the original function we're solving for, that f that's being mentioned above, and they gave us the second derivative. But we can do this, we just have to work in steps. First, we peel off a prime by finding an antiderivative. Question first.
So the f prime is 0, wouldn't that just be like, just plus 1?
What do you mean by +1?
Is like, y equals mx plus b, would it just be that initial value, wouldn't it just be b?
You're saying, are you mentioning like, say, the constants? Or
Yeah.
yes, we're gonna have a constant, essentially just 1 from that one.
Okay, so then with the second one, it's not a 0?
Exactly. This one, we're gonna have to solve an equation on. Exactly. I mean, we'll still solve an equation here, but it's really fast. There's a massive shortcut, all because of that 0, yes.
Does that work? So does it essentially go y equals mx plus b and that's b?
I'm not sure what you're meaning by y equals mx plus b, though.
Just like slope and then the x and then that.
So you're thinking some line coming through being
Right,
at
so
1?
that's at 0, that's the initial value, so that equals 1.
Well, yeah, the slope would be 1 for the tangent line.
I'm meaning that, like that b would be at the point 0, 1.
When you say b, what are you referring to specifically?
I'm not sure what it's called, but it's.
Are you saying the y equals mx plus b?
Yeah.
Sorry, I think I'm on the same page now.
Okay.
So this b right here, you're saying the b would be a 1?
Yeah,
Not necessarily. Well, it depends on what you mean. When we find an antiderivative, we're going to get a constant c, and that c would be a 1. But we're not trying to find the tangent line equation necessarily.
okay.
We're just picking up the first derivative when we undo this. Well, let me see if I have the right idea with your question. We'll form an antiderivative. It's f prime of x.
I was more meaning that it's like that constant tacked on at the end, kind of like the y equals mx plus b.
Yes, it is similar. Absolutely. Absolutely. So this constant here will be tacked on right here, much like this slope right here. But this b would have been a 0 because I drew it going through there. So we would have put in a 0 in that location.
So then with taking the antiderivative and having that constant, would that essentially be that prime is 0?
For this one, yes, because of the 0 right here.
Okay.
But we'll show the steps on getting through it because there's no guarantee it has to be a 0. It could be anything else. But did that answer your questions about that so far? Gotcha. Okay, well, let's give this a try. There's definitely a shortcut, really just because of that 0 right there. So good eye on that. When we go to get the antiderivative, pretty much what happens is this 3 is right where it is, stays put. Power next goes up to power 3 now, so x cubed. And that means we're dividing by 3 immediately. But if you thought of the check, this is probably how you might have written your answer. You might have said, well, we know the antiderivative of x squared becomes x cubed, so just write it in. Then imagine differentiating that. That would be a 3x squared if you differentiated it. It's automatically correct the moment you wrote in x cubed. So a lot of times people are thinking about the check even as they're writing down the answer to the first antiderivative term. So x cubed would go right here. This -1 is going to turn into a -x. And then we'll add a constant c. As we must, coming over here, we'll use this information only because the prime in this location means we use that initial value to solve for the constant. So let me write out here, f prime of 0 equals 1. Now the 0 again is special, but if there was like a cosine, a trig, a tangent function here, 0 might not have been as extra special. But for us, it's going to look like this: 0 cubed minus 0 plus the constant c equals 1. Means the equations are essentially just solved right there, right? This constant c is 1 just by simplifying the left-hand side. Then we come back over here and just fill in the 1. Now f prime of x equals x cubed minus x plus the constant 1. I'll put a check here just to remind us we finished out that initial value there. The next initial value is for the original function f. So we could have only used that. once we get our next antiderivative so far. Any questions at the moment, folks? Okay, let's get that next antiderivative. So now we're writing ordinary f of x. We know the new power of x is going to be 4, so let's lead with a 1/4 and write in x power 4. Then the next step is eyeball it for a moment. Imagine you're differentiating it. 4 comes down, it's 4/4. So yeah, you get 1x cubed. So that looks correct. Rinse and repeat. This one is going to be, first I'll put in the x squared. That means we should lead with a negative 1/2 to match that power. The positive 1 becomes plus x. And now here, you can make a choice. Some people say you ought to use a different constant c because we've already used the symbol c. Or we can think of the line in blue as being a whole different scope of the problem. And this constant c is only relative to f of x. Or you can just sideline all of that and just put in a different constant, call it d or c2. Really, you have a lot of choices on these. It's all a stylistic choice at this stage. But once we put in that constant d, we go to this initial value. We're going to use that information to solve for d on the next steps. Well, any questions, folks, at this step so far? Okay, let me rewrite that equation right over here. Now, f of -1 is 10. And that means I probably need a little bit more space. Let me put it down over here. That looks like an honest equation. F of -1 equals 10 means replacing -1 into this antiderivative. This will be 1/4. -1 power 4 is just 1, so we can skip over it. Same with -1 power 2. So 1/4 minus a half, -1 would go right here. Plus the constant d is 10. Now we can form a common denominator 4. Let me write this in as a 4 here, a 2 here. That would take us back to 1/2 if we simplified it. And we can call this one a 4/4, which goes back to 1. So let's take a look. It's 4/4 minus 2/4 plus a 4th. That should be -5/4 plus the constant d equals 10 or 40/4. So finally, d, when we add 5/4 to both sides, becomes 45/4. So close to simplifying, but didn't quite make it. That's okay. Sorry, say again. 11.25, awesome. Thanks for finding that. 11.25 is great, a nice exact value. It would be 11 for sure, and then there's a remainder 1. Yeah, I think you've got it. Awesome. You're much better at that than I am. I usually don't even try when it comes to these things, especially at night. Arithmetic is the first thing to go when you're tired. But last thing we have to do is write out, or answer is f of x as 1/4 x power 4 minus 1/2 x squared plus x plus 11.25. That last step is important. We have to write down what the original function is. But if you did it this way, you scratch that out and put 11.25 there, I would say that's okay. I would imagine you had d there first, found it, and you just didn't want to rewrite the whole thing. Well, that's the conclusion on this one, folks. Any last questions on this? Okay, well, we have time for just one more problem. We've got about 9 minutes or so. I think this will be a good last problem for us. It is an application, but it's a pretty fast application. It says a particle is moving with the given data. In our Calculus 1 class, our particles move in just one dimension. So imagine we're only tracking the height at time t potentially, or maybe just the distance along a path as time emerges, but only one dimension is being tracked. So this is the acceleration of that particle that's moving. The initial position is s at pi is 4, and the initial velocity at pi over 2 is 10. To get to this problem, here's how we would probably start organizing it. S of t is the position. And suppose you differentiate it. S prime of t equals v of t, which is velocity. And imagine if you differentiate that again, you would get s double prime of t, which is the derivative of velocity, which is back to a of t, which is acceleration. So that means if they give us acceleration, we can unwind all of this stuff. Let's make it happen right away. So the acceleration of this object is cosine t plus sine t. So lots of weird oscillations are happening to this poor thing. But we can find an antiderivative immediately. The antiderivative of acceleration is velocity. Why is that? Well, a of t equals s double prime of t. So if you find an antiderivative, sorry, I think I want that in black actually. So if a of t is s double prime of t, we can now immediately take an antiderivative of acceleration and go down to velocity. Velocity at time t is the antiderivative of cosine to start. That one is really, really tricky. Anyone see the antiderivative of cosine? Would it be positive sine or negative sine? We put down negative sine. Here's what I would do immediately with this function. I do that even these days, and I've been doing this for quite a few years. Derivative of negative sine, that would turn into a negative cosine. But we want a positive cosine, so all we need to do to fix that is just go sine like this. It always mixes me up when we're going from one end, differentiation, to the other end, antiderivatives. If sine, cosine, cosecant, there's a lot of sine work we have to be careful with. So same deal, anyone see the antiderivative of a positive sine? Let me show you the strategy I'd probably use. Sorry, say again? Let's give that a try. Maybe negative cosine? Let's give that one a try. Negative cosine of x. I'm going to put a constant c here so I don't forget it. If you differentiate negative cosine of x, negative stays put. Derivative of cosine x is negative sine. You have negative times negative. It emerges as positive sine. So good call. It's going to be negative cosine x on this one, plus a constant c. Well, we have an initial value for velocity. Velocity at pi over 2 is 10. So let's work that equation. I'll just copy it here just to remind myself what I'm doing. I'm working this portion of the problem. That means pi over 2 goes inside sine and cosine. Sine pi over 2 minus cosine pi over 2 plus the constant c is 10. Now back to the sine function. Sine at pi over 2 is a 1. Cosine at pi over 2 is a 0. Plus c is 10. So we can subtract 1 from both sides, and c equals 9. So we now know the velocity of this particle. If we never knew its initial velocity, we could have never solved this exactly. We would have just had infinite different possibilities for the correct velocity. But now we know our velocity is sine x minus cosine x plus 9 is the right thing to put in. Now that we're at velocity, we go and look up the velocity function. It's the derivative of position, and it said find position. So that's going to be our end goal on this thing. We're just struggling with some highlighting here. So this is what we're doing on our very last step. We'll look up our velocity function, and antiderivative is automatically s of t. That looks like the number 5. I really don't like s as a variable, even for a function. There we go. And then we just take antiderivatives. Antiderivative of sine, that's going to be the negative cosine that we did once already from here to here. So negative cosine x. But how about the antiderivative of negative cosine x? Should that be negative sine x or positive sine x? It turns out it should be negative. Let's take a look. Negative sine x. I could be wrong on this. I always, even if I don't write this out and emphasize it, you could watch my eyes. I'm eyeballing it to just double check myself. So if you differentiate this, it's going to be negative, staying right where it is. Derivative of sine becomes cosine. So yeah, we've got the right thing, negative cosine x. Checking as you go for some of these trig problems especially is a really good strategy, I'd say. Now we got through the worst of it. Antiderivative of 9 is 9x. We need a new constant. I'll label this one as d. just so it doesn't conflate in any way with the prior one, even though it's been solved. Now we have a position and we have an initial position, S at pi is 4. So we're just about ready to finish this one off. Any questions, folks, before we go to that last step? Okay, so let's write S at pi equals 4. So its position at time 3.14 is 4 meters away from its initial position, is what this is all saying, if meters was the unit. But what we're doing is plugging pi into the left-hand side of S. Excuse me, this right-hand side, I guess is the better way to say it. Becomes negative cosine at pi minus sine at pi plus 9 pi plus d, and then set all that equal to 4. Then this equation is not too bad. There's more terms, but cosine at pi is -1. So that whole first term turns into a positive one. At pi, sine takes the value 0, so it's -0, plus 9 pi, plus d equals 4. And then we're just about there, folks. We can now say that constant d is, I'll take the 4, subtract 1 from it, then subtract 9 pi from it. And we've essentially done it. Again, if you decide to just rewrite that value in for d, erase it and put it in, I'm completely happy with that and I understand the struggle. But that'll always look bad on the notes, so I'll write it this way. S of t equals negative cosine of x minus sine of x plus 9x plus 3 minus 9 pi. It's finally our end answer on this one here. So that's one of the nice applications of this kind of process, finding an antiderivative. And these kind of problems can get really kind of involved and amazing in a certain way, because your acceleration could be something like this, negative 9.8 meters per second squared. You could have an initial position, S at 0 is equal to 100 meters. You can now answer questions like, if you drop a rock up at 100 meters and you're near the surface of the Earth, where that is the acceleration due to gravity, you can find out how much time it takes for it to hit the ground, or what its velocity will be on impact when it hits the ground, and all sorts of weird questions. I did this question here only because it's more similar to the homework problem. But physicists love this stuff, but they're working at higher dimensions, so they combine it with more awful things as well. Other questions, folks, before we call it a night then? Okay, have a great night, everyone. When we come back on Thursday's class, it's going to be kind of a lighter class. 5.1 is not as big of a topic. It's kind of like our first day of class when we were in section 2.1. So if you have any questions related to the exam, I would be happy to help them out next class when we come back. Otherwise, have a great night, and we'll see you all on Thursday.